Okay, I'm back. Sometimes my computer doesn't like for me to hit pause, and so it instead clips the video. So that's fine. We'll have two videos. First one will be 25 minutes and 33 seconds long. And guess what? I figured it out. It's not hog, it's hawk. Totally different animal. So let's attack this one, see how it goes. Let's use brick red. Alright, so what's going on? This is H composed with K of X. So that seems to mean we're going to take K of X, which is this rational. We're going to cram it inside of H. So it's another compound fraction problem. Alright, whatever. Let's do it. Like I said, I kind of prefer thinking about, take the outer function, that's our shell. We're going to get, instead of x, we're going to get k of x. Downstairs, instead of x, we're going to get k of x minus 6. So here's h of x, just with all the x's turned into big empty spaces into which we plug k of x, which is this rational. So let's grab 1 over 1 minus x squared, 1 over 1 minus x squared. And it goes 1 over 1 minus x squared. And that goes. So there it is. That's your function. It's just not simplified yet, so we better simplify it. Step 1 would be leave the numerator alone. It's just 1 over 1 minus x squared. In the denominator, we need to bring these two terms together. So you get 1 over 1 minus x squared minus. Now this 6, that's a 6 over 1. If you multiply by 1 minus x squared over 1 minus x squared, you can generate a common denominator of 1 minus x squared. So this is going to be what? 6 times 1 minus x squared. The 6 would distribute in. I would get 6 minus 6x squared. Notice that rather than distributing the negative, right now I'm just leaving this expressed as a subtraction problem. That's why I'm not distributing in the negative. We're just leaving it as subtraction for the moment. Alright, now what? Now I shrink this to make some room, probably. Shrink. And I think you can probably still see that okay. So now on the next line, we still have the 1 minus 1 over 1 minus x squared in our numerator. Our denominator now, there's no getting around it now, 1 minus x squared. Up here I will have 1 minus 6. Now this minus for sure has to distribute onto both terms. So it'll be 1 minus 6 plus 6x squared. Okay, now some great news is we can cancel the 1 minus x squareds. And I don't know, it's kind of obvious why we can do that. If you think back to the previous problem when I totally explained that when you've got these complex fractions, just think of it as the numerator divided by the denominator, which of course becomes the numerator times the reciprocal of the denominator. Now if I do that here, then I get the 1 over 1 minus x squared times this reciprocal, so I get a 1 minus x squared in my numerator now, and this guy goes down to the denominator. What's this going to be, by the way? These look like common, these look like terms to me, so it'll be negative 5 plus 6x squared. I'll leave it like that for the moment. Negative 5 plus 6x squared. Alright, so this is where if I'm multiplying two fractions, then yes, I can just cross reduce. That's why those are able to be gone. So it looks to me like I'm going to land on a final answer of 1 over. Now here's where I hate this. See this leading negative sign? I don't like those. Those are bad. Especially when you can so easily just use commutative property to switch this order around. Just let the 6x squared come first and then go, technically it's 6x squared plus negative 5. That's just 6x squared minus 5. So there. I'm going to tentatively put a box around this, although my heart is already screaming out that there's going to be domain restrictions that we need to list. The fact that 1 minus x squared canceled out, well, that would be 0 at 1, wouldn't it? that seems to me like that's going to be one of these non-obvious domain restrictions that we need to actually sweat. Okay, but for now, hopefully you at least understand where this function rule came from. Here's the rule. This expression so far is great. So how's about I grab it, shrink it down just a smidge, just to make a little more room so we can think about our domain. All right, so again, if I'm a lazy fool, then I might say that my domain of H composed with K is nothing more than the domain of this algebraic rule right here, which of course would be all reals except for whoever makes the denominator 0, which of course would be 6x squared minus 5. Well, I can't let u be 0, and then you just solve this equation. So 6x squared equals, or shouldn't equal, 5. So x squared shouldn't equal 5/6. So x shouldn't equal plus or minus the square root of 5/6. Which of course, as you all know, would be plus or minus the square root of 5 over the square root of 6, which you could rationalize by multiplying by root 6 over root 6, which would generate a slightly more acceptable form, plus or minus root 30 over normal 6. Or, or you could just leave it as plus or minus the square root of 5/6. But I don't know. Mr. S not down for this whole radical in the denominator thing. So technically, those are our domain restrictions. But again, these are only your domain restrictions if you're a lazy person who doesn't fully understand how composition works. So I'm going to write this down. My domain is all real numbers except for plus or minus. And I also don't kind of love plus or minus. I'm going to actually list this as two things. I'm just going to go negative root 30 over 6 and positive root 30 over 6. There's no reason to do that other than I want to really drive the point home that there are two domain restrictions. Or are there? Maybe there's more, right? Because technically, the way I'm really supposed to do this is I'm supposed to go all the way back to the original definition of the function, and I'm supposed to consider that inner function k. And what is the domain of function k? Well, function k has a 1 minus x squared in the denominator. That, of course, is a difference of squares. It's 1 minus x, 1 plus x, which certainly would seem to indicate that it is undefined at 1 and negative 1. So those domain restrictions, those carry through. No matter what happens here algebraically, those discontinuities at negative 1 and 1, those values that make us undefined, they still can't be in the domain of our composition since they're not in the domain of k. All right, great, fine. Anybody else I need to worry about? Well, 6 is bad, right? So any value of x that function k maps onto 6 are bad. The good news is we could do the algebra to figure out what those values are, but I got a pretty strong inkling that maybe it's plus or minus the square root of 30 over 6, right? But again, if you really were dead set on doing this math, you'd say, hey, 1 over 1 minus x squared, I need you not to be 6. And then you solve this equation. And you'd solve it probably by just cross multiplying, so you'd get 1 should not equal 6 minus 6x squared. And so then you'd subtract 6, I'm sure. You'd get negative 5, but then you'd divide through by negative 1 to get positive 5 should not equal 6x squared. At which point I'm just going to quit because you should probably be noticing that we just arrived at the same point that we were already in when we already did this math before. And yes, we're going to land on plus or minus root 30s over 6. So I'm happy with this. I'm ready to now say that I shouldn't say happy. I struggle to say that I'm happy about this, but it does seem like our actual domain is going to have 4 restrictions. and those 4 restrictions. Now who's bigger or who's less? I did say we're supposed to go in numerical order. So is this thing worth more than 1 or less than 1? Obviously the square root of 36 would be 6. So this is smaller than 6, which means this is smaller than 1, which means negative 1 is my smallest restriction. Then the negative root 30 over 6. Then the positive root 30 over 6. And then the 1. Of course, you guys can go hog wild with your plus or minuses, but I'm going to leave it expressed this way because this so strongly indicates that our domain has 4 restrictions. Ooh, my face almost got in the way. Let's just move that over so you guys can see the end of my box. All right, we did it. So E was no joke. This was a pretty complicated problem, and it left no room for K. So let's do this. View, browses. This page gets duplicated. Duplicate. Come on. Okay. Then we'll clear everything. Go on, and we'll start again. All right, E, you got done, so you're out of here. Just hide that behind my face. Let's do F. All right, so F is K of F of X. So again, using that notation we've been using, this would be K composed with F of X, whichever notation you want to use. This means we're taking function F, meaning this rational with a radical, and we're cramming it into function K, which is this rational with a quadratic. So this is another one that seems like it's, going to be a hot mess. So I'll take K as my outer shell. I get a 1 over 1 minus an X that is squared. I shall now take F, and I'll cram it in where the X used to be. So 1 over root X. All right, doesn't look so bad just yet. So this is 1 over 1 minus. Now from squaring this, I square the numerator, I square the denominator, I get 1 over normal X. Okay, great. So that becomes, let's see, 1 over. This 1 I would treat as a 1 over 1, but I need it to have a denominator of X, so I'd multiply it by X over X, and it'll become X over X. So I now have X over X minus 1 over X. That now becomes 1 over X minus 1 over X. And luckily for y'all, treating this fraction bar as sort of our main fraction bar, 1 over a fraction is always just the reciprocal of that fraction. You can take for granted that 1 over A over B will 100% of the time just be B over A. That's a fact. So you know that this is just going to be X over X minus 1. Oops-a-daisy. So it just dawned on me. That nightmare of a problem from before, this algebraic expression, I mentioned this and then I didn't go back and do it, but shouldn't we be stipulating those non-obvious domain restrictions? And luckily for us, the non-obvious ones are the ones that are clean. That's the plus or minus 1. The root 30s over 6, you don't have to stipulate those because those are actually already air quote obvious from the denominator that we still have. But technically you should be coming back here and saying, why is this thing still so giant? Oh yeah, bonk. Okay, comma, X cannot equal plus or minus 1. Okay, sorry. Part E had to come back and haunt us one more time. So make sure you actually list, and look, I get it. I know that you're listing them down here, 1 inch away, but you're still supposed to build it in to the actual algebraic expression itself. I see them, I know they're right there, but they should be here too. Just do it. I'm your teacher and I said so. All right, moving on. Hey, look, we did it. I still have this sort of aching in my heart that says this is not going to really be good enough. I bet there's secret domain restrictions here that we're going to have to address, but you know, I'll leave this one alone and I won't forget to go back. All right, so again, if I'm lazy and if I don't really understand math, then I might say that the domain of K composed with F is nothing more than all numbers except for the number 1. Because that's how rational functions usually work. Usually it's all numbers except for the 0 of the denominator. I'd probably even walk away from my quiz feeling really good about myself and thinking I did great. But I would not have done great if I do that, because let's not forget, this function is defined as a composition, and all those rules for compositions still apply, which means I have to look at the domain of F first. And the domain of F says, you can't even be negative, and you can't be 0 either. So we are immediately limited to 0 to infinity, which is a hell of a lot fewer domain elements than this, right? So yeah, if you did this, you're totally wrong. Do not base your answer on this. That's the moral of the story. You can't go off of the algebraic rule that you generate. You have to come back to the original definition of the function and really think it through. Oh, by the way, are there any further restrictions? Geez, I don't know. Let's think about function k. K says we can't be 1 or negative 1. Remember that? Because in factored form, this is 1 minus x and 1 plus x. So 1s and negative 1s will cause us to be non-real. So that means we better grab function f, 1 over root x. We better set it equal to 1. And we better do 1 over root x and set it equal to negative 1. We've got sort of two separate equations here we got to solve. So let's do it. I would just cross multiply probably. I get 1 equals root x. I guess I square both sides and I get 1 equals x. Okay, so it turns out 1 actually is the input that maps onto 1. I don't love that. I think these problems are a lot more interesting when we know that 1 is bad and then it turns out that like 7 is the thing that maps onto 1. Just remember that step happens, and the fact that 1 maps onto 1, it's not a coincidence, but it's sort of an unhappy result here. It's a result that might cause you to not fully understand the situation. But hopefully you do. Anyway, 1 is bad. Hey, and guess what happens over here? We get 1 equals negative root x. And then we square both sides and we get 1 equals x. So 1 is bad again. What about the negative? I guess what's happening here, of course, is that because we're squaring both sides, the negative gets washed out, and 1 over root x is just a function that is never going to return negative 1. So we don't have to worry about that domain restriction on k, the negative one, because f of x will never map onto it. I'm going to take this risk and pause the video again. Okay, I have unpaused. We seem to still be rolling. Okay, ready? Magic. Desmos is here. Here's that function, that 1 over root x. You can see that our domain is restricted to only those things that are greater than 0, like we already said. And you can also see that what we're getting is what looks to be a branch of a hyperbola. It probably isn't truly a hyperbola, but I'll call it that anyway. But look, it never goes below 0. So does it return the number 1 at some point? Of course it does. It seems to... Yeah, it returns 1 at 1, like we already saw. 1 maps onto 1. But obviously we never get negative 1 because this graph has a horizontal asymptote at 0. So we don't have to worry about that restriction. Okay, was it worth it to say all that? I don't know, probably not. Okay, I'm going to move that away now. Nope, I didn't. That can go here. Alright, go away, Desmos. Alright, anyway, this turned out to be a pretty interesting question because it turns out we do have some domain restrictions that we would have missed, but those domain restrictions don't actually end up coming from k of x. They're really actually all completely covered. Well, they're not all covered, sorry. f says we have to be greater than or equal to 0. Strike that. We have to be strictly greater than 0. And k does have that one stipulation that says it won't take an input of 1. And since this function has an output of 1 when x is 1, we do have to pluck out the 1. So our final domain would be 0 to 1 union 1 to infinity. So okay, again, that means this is bad. And that does mean that our original expression is really not great. So what's our domain? The domain of k composed with f. We just said it's going to be 0 to infinity. That's to satisfy the domain of f, but then also no ones. And the no ones thing, I don't want to keep repeating myself, but I'm going to say it one more time. The no ones thing is because if you plug in 1, that has an output of 1. Then you try to plug 1 into k, and you're undefined. So the 1 is bad. So that's your domain. So what do I have to do over here? The thing that's sort of missing here, the thing that's not obvious at all, because the radical got washed away when we squared it, is the thing about how x's can't be they can't be negative. We need them to be non-negative. So I think we just have to stipulate that x has to be greater than 0, like that. I don't have to really address the 1 because again the 1 is already obvious from the domain. But you would have to stipulate here as part of your function rule that this expression is only equivalent to this function. It's only equivalent to the composition if you limit your domain to the x's that are greater than 0. And oh, by the way, of course you can't have 1 because that would cause us to be undefined. So there. I'm going to put a nice orange box around both of these. And that would be the final answer to both parts of number 1, part F. Can that be it? I want this to be over. Oh, we have 2 more. Great. All right. What are we pulling up on? 50 minutes of math and we're not even out of number 1 yet? All right, well, you kids better watch it, and then you better put a comment down that says, hey, thanks, Mr. F, I appreciate it. Literally the least you could do. All right, hey, let's do another one. Why don't we take function m and cram it inside of function k, generating the expression 1 over 1 minus 2x plus 1 squared. Then, why don't we clean that up so it's 1 over 1 minus. All right, I hate that I have to go over foiling, but I'm going to go over foiling just in case. 2x plus 1 squared is 2x plus 1 times another 2x plus 1. So please stop thinking that this is simply a 2x times a 2x, which is 4x squared, and a 1 times a 1 giving a 1. Don't forget there's the middle terms. We have to do the outers and the inners. So the 2x will multiply by the 1 and give me a 2x. And then the 1 will multiply by the 2x and give me another 2x. We're going to get these 2 middle terms. So you're looking at a 4x squared plus 4x plus 1. That will be the expression that results when you square this binomial. So 4x squared plus 4x plus 1 in parentheses so that the negative can distribute into all 3 of the terms of this trinomial. And that'll lead us to a 1 over a 1 minus a 4x squared minus 4x minus 1. That'll lead us to needing more space. So after that lavender colored step, you now have 1 over negative 4x squared minus 4x. And of course 1 minus 1, those cancel out. So at this point, I'm not loving the way this looks. I can definitely clean this up more. I can clean it up more by factoring out of my denominator. I think it's obvious that I can factor out a 4. It should be obvious that I can also factor out an x. And it should probably be obvious as well that I can factor out a negative, because I don't really like to have these leading negatives. So let's factor out a negative 4x leaving behind what? Just an x and a plus 1? And you better give me that. The only thing you might do here, which I think is sort of worth doing, is just move the negative. This negative could just be a negative applied to the whole fraction rather than a negative that seems attached to the denominator. That's kind of weird. I would just say this is 1 over 4x times x plus 1, and it's the opposite of the whole thing. I know the change I'm talking about seems kind of silly, but it's kind of weird to just have a negative attached to the denominator rather than a negative that's attached to the whole fraction. So I would do that. All right, great, we did it. So what's our domain then? Well, if we are fools who only base our answer on the algebraic expression that results from this work, then we would look at this and say that our domain is all reals, with the exception of these two zeros of the denominator, which of course are 0 and -1. Alright, and if the past few questions were any indication, we know that's not going to be the case. Maybe it is. Let's find out. We know that when we find the domain and range, we're really supposed to be first considering the inner function, which is m, which very clearly has a domain of all reals. So that doesn't actually generate any restrictions. Then we look at k, and we remember that k will not accept plus or minus 1. So doing this math the long way, we would just take function m, the 2x plus 1, and we'd go, well, you can't be 1. And we'd go 2x plus 1, and we'd go, well, you can't be -1 either. And technically, you've got two equations you need to solve. So solving them, I mean, this is literally the easiest thing of all time. You get 2x equals, subtracting 1 gives 0, x is 0. So 0 is a restriction on our domain, and would you look at that? We already knew that from our algebraic rule. And over here, you get 2x equals, or technically I should say, should not equal, -2. And dividing by 2 says x should not be -1. Hey, look, it's the other guy that we did already know about. So for this problem, if I did this problem the wrong way and just kind of trusted the algebraic rule that I generated, I'd actually be fine. But that is the exception and definitely not the rule. So the domain of k composed with m is just going to be all real numbers except for the two zeros of our denominator, -1 and 0. So why'd that come out so simple? I'd like to think you can guess why it came out so simple. It came out so simple because that inner function was a function that had no domain restrictions anyway. So the two domain restrictions on k ended up just kind of becoming obvious. Remember, the ones that were complicated were the ones where we were plugging rationals inside of rationals, and they involved radicals as well. So there was a lot that could happen algebraically that would mess with our perceived domain. But not here. Here the algebra was pretty straightforward, and none of the domain restrictions got lost by any of the steps we took. Okay, cool. Moving on. I want to make room for the next problem again, so I'll duplicate this page, and then I'll delete everything, and we'll hide G over here, put H over here. Alright, now we get down to business. Hey, look, we're taking m and we're plugging it into a quadratic, so that means I'm starting with a guy whose domain is all reals, and I'm plugging it into another guy whose domain is all reals. Seems a pretty safe bet that this one is going to be very straightforward and that the ultimate domain is just going to be all reals. But, you know, let's do it anyway. So what did I just say? I like to do this approach of taking the outer function and just kind of making a shell out of it. Instead of x squared, it's going to be all of function m squared minus 3 times, not x, but all of function m, and then minus 4. Alright, so if m is 2x plus 1, then I need to literally take that whole function and plug it in where the x used to be, right? And then I have to do that for all the x's. So 2x plus 1. I guess I need another one and plug it in for this x. There you go. So this now is our function rule. Obviously it needs to be cleaned up. We have already taken the 2x plus 1 and expanded it. So we should hopefully already know that this is about to be a 4x squared plus 2x plus another 2x, so plus 4x, and then plus 1. We should certainly know by now that this negative is going to distribute with that 3, so you get minus 6x minus 3, and then you just have this straggling old minus 4. Alright, now we just combine like terms. I will often kind of underline things. I'll say, okay, there's only one quadratic term. Here's an x term. I'll underline that twice. X term, x term. And then, I don't know, here's a constant, constant, constant. You can do something like that. That's what you would do if you only had your pencil. If you had a highlighter, then you could be nice and careful here and say, all right, I got a quadratic term here. I got a linear term here and another linear term. And then I got a constant, and a constant, and a constant. So now it should be pretty easy to, very quickly pull out those like terms and combine them. So you've got a 4x squared minus 2x. Minus 2 minus 6. Okay, great. You're not done because there is a greatest common factor here among these terms that you can factor out. It's a 2. They're all even, so obviously you can factor out a 2. So factor out a 2. And then you get a 2x squared minus x minus 3. Okay, I'd like to say we're done, but there's a good chance we're not done, because even though you kids might not be good at it yet, sometimes quadratics that have leading coefficients can be factored. If you guys are like the kids I've had in the past, then you like to try to factor these using that method of grouping. So sure. Don't forget I've got this leading coefficient of 2. I'm not abandoning that, but I am going to grab only this other stuff, the 2x squared minus x minus 3. I only need to factor that. So you might remember that the trick here was you have to take the leading coefficient, which in an equation like this, or an expression like this, ax squared plus bx plus c, you're taking the a value, you're taking the c value, and you have to multiply them. So 2 times negative 3 makes a target of negative 6. We're looking for factors of negative 6 that add up to the b value in the middle. And guess what? It's literally the 2 and the negative 3 themselves. It could have been a 1 and a negative 6, but that makes negative 5. Could have been a negative 1 and a positive 6, but that makes positive 5. Could have been a negative 2 and a 3, but that makes positive 1. But this is literally all the possible pairs of integer factors of negative 6, and it is that one. So you probably learned to take this middle term and express it as the sum of these guys here. So plus a 2x minus a 3x, and then the minus 3. So you're literally splitting that middle term. And the positive 2x minus 3x is equal to negative x, so we haven't changed anything. So now what you did was you grouped the first two terms and the last two terms, but notice that technically here you need this to be plus the negative 3x, and then you can group them. Okay, but now you factor out the GCF, which is 2x, to be left with x plus 1. And here you factor out the GCF, and leave this as a sum, by the way, it's plus. And then you're factoring out what, a negative 3? I like to put my negatives in parentheses so that the negative doesn't get lost. But this would be x plus 1. And of course you immediately notice that these are the same. If these weren't the same, then it means we're not actually factorable. But since they are the same, then essentially what you do now is you're now factoring that out. The x plus 1 is your common factor. So you factor out the x plus 1 and you're left with the 2x plus negative 3, aka minus 3. But that's it. We did it. We factored this red thing down to this, which means our final answer over here should be 2 times, I'm going to put the 2x minus 3 first. There's no rule that says I must, but I'm gonna. And then the x plus 1. So that's just algebra. I mean, that wasn't pre-calculus that happened right then. That was just algebra. And I get that it was some heavy algebra, but you should be okay. Anyway, the good news is the domain's a piece of cake, because like I said, the domain of G composed with M, even just as you look at this expression, this is still just a quadratic. So your heart should assume it's going to be all reals. But again, be careful. Don't trust the rule. We've seen plenty of rules that had sort of secret hidden domain restrictions. This guy doesn't, because as we already said, looking at the inner function M, his domain was all reals. Then looking at the outer function G, its domain was all reals. And so, no, there were no values that we needed to restrict from the domain of the composition. So there you go. There is your function rule, ding, and here's your domain, ding. All right, and 1 hour later, we have done one math problem. Let's do more. All right, so these I think were cake. I don't know if any of y'all were stuck on these, but let's try it. So we are being asked to decompose these expressions with G, the inner function. So one way to decompose this, I certainly see an inner function here. The stuff under the radical makes a good inner function. So I'd let this be x squared plus 7. Then the outer function would be the radical minus 8. And just make sure you just put plain old x under the radical as a placeholder for where g of x would substitute in. But that's it. This is one possible decomposition. I've kind of spilled the beans on this. I think the other teachers have too, I hope. That you will be expected to be able to decompose this in more than one way. But I don't think this one can be. There's got to be a way. Oh yeah, of course there is. Another way to decompose it would be is just let the inner function be just the x squared. Then that means here you would just need a placeholder x for the x squared, but the plus 7 would still be under the radical. The minus 8 would still be outside. And then I'd be taking the g of x, substituting it in for the x and getting the right thing. So I'm sure there's other options too. These decompositions are probably never ever unique. There'd be more than one way to do it. So as you do these problems, do be thinking about other ways to maybe more creatively decompose than just taking the entire radicand and turning this into root x. All right, this one might only have the one way to go. I'm not sure, but it probably jumps out at you that the 2x plus 1 is an inner function. And then luckily we've got another 2x plus 1 here. If this wasn't 2x plus 1, if I wanted to be a real jerk, I could give you like even just a 4x plus 2. And if I gave you 4x plus 2, you might not immediately notice that you could just factor a 2 out of that and then make it a 2x plus 1. And then it would be decomposable. But certainly this one is not that bad, since it literally says 2x plus 1 and then it says 2x plus 1 again. I think your eyes can probably pretty readily key in on that as your inner function. So that's going to be your g of x, the 2x plus 1. And then, okay, that means this would be 3x squared. And this will be plus 2 times the sine of x. And then a minus 20. And then that would do it. This thing would be decomposed. Is there another way to do it? I don't think so. Well, yeah, there is. We could do 2x. G of x could just be the 2x. And then you'd make this x and make this x. And then the 2x's would slide in there. So yeah, there is another way to break that down, but beyond that, I don't think there's much. So I'm going to leave that alone. We're going to move on. All right, this one. So again, your eyes should probably just fall on the 5x squared as being a good inner function. So you just let g of x be the 5x squared. And then you let f of x be e to the power of the sine of x. And that'll do it. Any other way to break this down? Sure, lots of other ways. You could actually let sine of 5x squared be the quote-unquote inner function. This doesn't look much like an inner function, but it is. And then the outer function, so to speak, would be e to the x. And so you'd take the g of x, you'd substitute it in, and there you go, you'd have it. So there's a second way to break that down. There are others, I won't share them all. All right, what about this? All right, great. I wish we had done that trick here of actually kind of disguising this. Maybe just for the sake of argument, we'll talk about it now. So what if this wasn't x plus 5? What if this was instead 3x plus 15? Hopefully you would notice, oh, okay, that's just x plus 5 times 3. So this would be the ln of x plus 5. You could pretty quickly just break this down to 3x plus 5. And then you could still use the x plus 5 as your inner function. Let that be your g of x. And then let your outer function be the ln of x minus 2 times 3x squared. And I'm realizing I put an x up here. That's just squared. All right, but there you go. You can see how this, would be a little trickier if we sort of tried to hide that inner function from you. But I'd like to think you'd be wise to that little trick and catch on just fine. All right, moving on. This stuff. Yeah, you definitely got to know this graphical stuff now. So let's do that. Maybe everything in purple. All right. So it says, use the graph to determine the following. F minus g of negative 1. Remember, the meaning of this is that it's literally just, I don't like that. It's just f of negative 1 minus g of negative 1. What am I doing? F of negative 1 minus g of negative 1. So f is the red function. I did not get that backwards, right? So to kids in my class, I might have given you one where these are mislabeled. Maybe they're calling this one F and the other one the other one. If it's like that on your paper, scratch it out and fix it, or just adjust in the way you see fit. But f of negative 1 means we're reading the red function. Negative 1 on the red function yields 3. Then we subtract from that g of negative 1, which means we're now reading the blue function, and negative 1 yields 1. And guess what 3 minus 1 is? It's 2. It's as simple as that to evaluate these expressions. You just find f of negative 1, you find g of negative 1, you subtract them. That's it. Okay, what about the other one? F is the red function. So I want to do f of whatever g of 4 is. G is the blue function. So g of 4 means go to where there's 4. Read off the blue function. It's 2. So you're just trying to evaluate f of 2 now. So now go to where 2 is. Read off the red function. It's 0. F of 2 is 0. That's it. So again, f is red. This notation just means do f of negative 1 and divide it by g of negative 1. And of course, if I'm reading the blue function, then g of negative 1, let's see, negative 1 gives 1. So 1 in my denominator. F of negative 1 gives 3. And 3 over 1 is, shockingly, 3. Okay, you didn't come here for those 3 questions, I'm sure. You probably came here for these. So it says find the domain and range of these functions. I honestly think that we don't really care about range. But let's maybe talk about it anyway. Let's do domain first, though. Let's find the domain of f composed with g of x. So as we've said, ad nauseum at this point, you must first find the domain of g. And the domain of g should be obvious. I mean, this is a square root function. Specifically, it's the square root of x. Let's see, it looks like someone dragged it to the right by 5, so plus 5 under the radical. It looks like someone dragged it down 1, so minus 1 outside of the radical. You should be able to do that, I hope. So what's the domain of that thing? Same as everything else. It's going to be -5 to infinity, but not including the 5. Same old rules for radicals. Okay, I'm not so interested in the domain of f, especially since the domain of f seems to be all real numbers anyway. So are there any outputs of function g that are not in the domain of f? Well, clearly not, since f has a domain of all reals. Just as a fun little activity, what is this graph's equation? It certainly looks like a parabola that somebody just flipped upside down, so I bet it involves -x squared. But it also looks like somebody translated it 4 units up, so I bet it's -x squared plus 4. You kids should be able to do that. Write the equations given the graphs, at least for fairly simple ones like this. So what did I just say? I think I just said that the domain of f composed with g is just literally equal to the domain of g. Because that outer function f, had no domain restrictions at all to worry about anyway. All right, the much more interesting question now is g composed with f. So we will certainly start by considering the domain of f, which I just told you is a quadratic, which you should probably know has a domain of all reals. So there's no restrictions at that first part. But wait, we can see that function g certainly does have domain restrictions. It says it will only take inputs that are greater than -5. And looking at function g, we very conveniently included these dots at -5. And we can see that for values of x that are less than -3, we will get outputs that are less than -5, and therefore they will not be in the domain of g. But also, for values of x that are bigger than 3, we're going to get outputs that are less than -5. So those also cannot be in the domain of g, which means we absolutely do have further domain restrictions based on function g. In the domain of g composed with f will be only those values of x that lie between these two values here, so between -3 and 3. Now is -3 itself okay? Yes, it is, because -3 maps onto -5, and then for g of x, -5 maps onto -1. It does have an actual output. So both of these should be included. It would be hard bracket, hard bracket. Okay, hope that made sense. Oh, there's more. A lot more. Okay, that's fine. Let's do it. Number 4. Is my thing still going? Still going. We're up at 50 minutes. I better get at least one thank you. Swear to God. All right. Hey, everybody. What is g minus f of -3? Geez, I don't know. Could it be g of -3 minus f of -3? And to evaluate those, do I just read the table? I think I do. So f is this lavender colored function. So f of -3 is -3. You just read it off the table. And g is this mint greenish colored row. So -3 is giving -5. That's too mint. I need less mint and more forest. Okay. And we're subtracting these things. You guys are good at subtracting signed numbers, right? You guys don't ever screw this up, do you? This is a -5 plus a 3. That's a -2. Nailed it. All right, how do you do this? Do you do g of 4 and divide it by f of 4? You do. Do I have to keep color coding this? I don't want to, but I will. Function g is the green one. If I go to 4, that's giving 0. So the denominator is irrelevant because I'm gonna get 0. Well, unless f of 4 is also 0, in which case I would be, for now we can say it would be undefined. In calculus, you'll say 0 over 0 is something else. But f of 4 is the lavender colored function. 4 gives -1. And so we are just 0. Okay, again remember, it's if the 0 is in the denominator, that's when we would be undefined. And an expression like this will never be does not exist. Does not exist is only for limits, remember. Alright, so for this one, this is not composition, this is just multiplication. So you're just doing f of -1 multiplied by g of -1. And function f is the lavender colored function. -1 yields -7. And then the other function is the green function. -1 yields -2. Which seems to me to give a final value of positive 14. Okay, this one, I need f of 1 plus f of g. Okay, that's not right. I need f of 1 plus g of 1. And if f is the periwinkle colored function, then f of 1 is giving -7. And g being the green 1 is giving 4. And if you add those up, then you're going to get -3. Those are straightforward, in my humble opinion. Now we've got some compositions going on, so maybe this is less straightforward. Let's find out. Okay, of course, f being the periwinkle colored function, f is going to wait, and we're going to see what g of 7 is. That's the green. 7 is mapping on to -2, so we need to do f of -2. So we find the -2 as our input. We're reading off the periwinkle, so it's -5. Hopefully that's obvious. All right, what is f of 7? Let's see. F of 7, 7 gives 5. So I guess f of 7 is really f of 5. So I find the 5. Oh, there's no 5. What on earth could I do? Well, we're undefined then. Because no, you're not supposed to just extrapolate some value. Since 5 is between 4 and 7, you're not supposed to extrapolate that it's something in between. If this function is defined as a table of values, then you should be assuming there's nothing in between. You should be assuming that function f is just this random smattering of points. And so if there's no point assigned to 5, then you're just undefined, which hopefully makes sense. All right, g of f of 1. Let's see, that would be g of f of 1, 1, f, -7. G of there's no -7, so again we are undefined. Okay, and f of g of 4. Let's see, that'll be f of g of 4, g of 4. That's 0. Why am I doubting? All right, and again, there's no 0, so they're really hammering us over the head with these undefines. What I don't like about the fact that they gave us 3 undefines in a row is that none of them failed in sort of the first round. We could have failed in the first round by just asking something like A, B, C, D, F, G, H. We don't like to ask I, so I will skip I and go directly to J. What if there was a J that asked you for f of g of 10? Well, you can fail immediately. If there's no 10, then I'm asking you for f of a thing that is undefined, which of course makes the whole expression undefined as well. So in all of these, we got through the first round, so to speak. F of 7 existed, it was 5, but then we were undefined. F of 1 existed, we were -7, then we were undefined. I never know. So just be aware that, of course, something like this could happen too. That's it. I have nothing more to say on the matter. I don't think. And guess what? I've said plenty. It's 55 minutes of free math tutoring on the black market. That would go for over $100, right? Okay, you're welcome. Have a great night. See you later. Bye.